So, any questions about this, what we have been talking about for a short while? So as you can see, it takes like a couple of pages, but it just contains so much stuff in it. It is literally, well, just 2 pages of writing, but certainly by no means it's an easy topic. So inverses, compositions. So we started with composition, then we interpret inverses as in terms of compositions, which is crucial because some of the ideas are intuitive and you carry them on from calculus, but then when you look at them in a more precise way, then your intuition might kind of start to fall apart. So try to keep the things that you do remember from calculus. I don't know, say exponential function is the inverse of a logarithm and vice versa. Things like that. Or how do you build the inverse of a sine function, which is not one-to-one, or things like that you've seen before. Or that example on the right. So as you can see, I picked only one example from the whole calculus, but certainly inverses appear, compositions appear a lot in calculus. So I do expect you to connect, make that connection on a lot of it on your own. And we're looking at examples that are abstract, but that does not make them necessarily more complex, because these pictures, that picture is actually quite complicated. That example from calculus is kind of complicated. And I don't want to. I do try to visualize it with a diagram, as you see in the middle. But that diagram might also look kind of more complicated than it is. All of these ideas can be illustrated with very simple diagrams. Why? Because, well, we're not in calculus anymore, so if we can make it simpler, we could. Okay, and by that I mean that when you talk about calculus, the domain, codomain are real numbers. For example, is calculus 1. So there are infinitely many of them. Okay, so you start thinking about function, its inverse, and you immediately start at the real numbers. Okay, but that is already complex. So how about when you go to simpler ideas? So you can, how large does look at f from x to y? How large does x have to be? It's a set. How large does it have to be? How many elements does it have to be? At least. What? What? 2? 1? It doesn't matter, as long as you don't say the infinite, then you're fine. You're close enough. Close enough. So the point is, I was trying to make a point. That was a rhetorical question, and so I got my answer. So you can have 1 or 2 elements, and it's still all the definitions still work. So calculus is more complicated that way. So always everything is infinite. Okay, it doesn't have to be. So you can literally have compositions of functions. X consists of 1 element. Y consists of 1 element. Okay, the function still makes sense. And you can, if Z consists of 1 or 2 elements, then your still composition makes sense. Okay, there is no requirements of any kind of particular infinity somewhere or number of elements that required for these. Absolutely no difference. Where the difference does make something to worry about, it's one-to-one onto. Okay, so we have. Let me illustrate that with the pictures that we saw. Well, this is a calculus example, and it is in fact more complicated than it has to be. We have one-to-one functions in onto that. Those pictures on the right that kind of feel like visualization, but really you can think of them as actual functions, examples of functions that violate the property. Okay, so for example, we're talking one-to-one. Literally, I am making x consist of exactly 2 elements. Okay, A and B. A and B, and then what happens under f? They go to element C. So this is the whole x is A and B, nothing else. And then they go to element C in Y. So this is the whole x, this is the whole y, and this is what you have here is not a visualization. This is a literally example of 2 sets and a function. Okay, so it is we visualize it with arrows, but really you can actually write it out in the sense, say f of, if I want to write it complete, incomplete, what would I do? I would do what? I would just write so x is equal to ab, two elements. The nature of elements don't matter. Y is equal to one element, c, okay? And then f of a is equal to f of b is equal to c. So that's an example of a function that's not one-to-one, with literally only two sets. Naturally, one function in there, but those two sets, one consists of two elements, the other one consists of one element. Okay, and then you have a perfect illustration of function that is not one-to-one. How do you function? What is the easiest example of function that is one-to-one? The easiest example.
Y equals x. Just like a line.
Simpler. They're like this. As simple or simpler than this. 1 point to 1. Two sets. 1 point, that point goes to that point, the end. That's a one-to-one function. It's also onto, and it's a bijection. All of these exemplified, all of these ideas are exemplified by this especially trivial example. Okay, same thing with the other one, the function that is not onto. So the example for the next one. So I flip. Well, maybe you can tell me, how do I illustrate an not onto function with as few elements in the sets as possible? So I need x, I need y, I need f. Look at the picture on the right there at the bottom, on the right. Well, in fact, it has, look at it. It has too many. It has way too many. Why do you, I mean, you want to make that point, but was I trying to make when I made that picture to make a point, kind of more, but it's over dramatic in a way, because there you need to violate, not to be onto, you need to violate that property only once, and that's it. So once again, so what's the example of a function that is not onto?
X has 1 point, y has 2 points.
Okay, that's right. So yeah, that's right. So this is, say, BC. F of A is equal to, say, Bn. Okay, so in other words, one element goes there from A to B, but then there's one more element that is, and we don't have anything for it, like this, x, y. So an example of a function that's not one-to-one. Not onto. Okay, so it could be simple, and so every time you see a new idea, test it on really, really simple examples. It usually helps. So once again, the examples from calculus that I try to bring up many times, they are way more complicated than they have to be to illustrate the simple ideas. Certainly, the ideas that we have, we want to then expand it to and apply it back to all of those other disciplines of mathematics, such as calculus. But it is okay to look at this. So when, for example, you need to have an example or counterexample of something, that it doesn't have to be complicated. You feel free to make it as simple as you like. So let's go over these ideas and once again see if we can simplify things. Okay, so this one is a composition, right? So composition. Like I said, compositions. Once again, there are no requirements on the set on the sets involved in order to form a composition. So it could be one element, it's still composition. Okay, so that's not it, composition. Okay, and one-to-one onto bijections. Now inverses, the number of elements, well, that is, I hope, is transparent, especially when we talk about finite sets. This one is the inverses. Well, so once again, to illustrate that idea is you can illustrate it with only one set, set with one element. Both sets have only one element, and f of A is equal to f of B. F of A is B. F inverse of B is equal to A. That's it. Okay, so that's the whole example of the inverse, when there is only one element, like I said, in every set. So it could be simple. Okay, so all right. So the inverse is what you can verify it. I mean, this is, since there are only two elements to worry about, then I have to only these to write up. But you can certainly verify that if I do the composition, I go under F, I go from A to B, and then I go from B to A backwards. So I make a complete circle. Or I start with B, go to A, and then go backwards to B under F. So once again, the circle is complete, and that picture on the left is pretty much the same as on the right, except for those little ovals that I drew to indicate that there might be more points, but really doesn't really matter. They don't have to be there. So it could be as simple as what I have on the right. Okay, and now we're talking about making sure that we want to discover under what circumstances function has the inverse. And we have, we more or less, we demonstrate here that when the function is not onto, there is no inverse. When the function is not one-to-one, there is no inverse, and that takes us back to what I just talked about a minute ago. You can verify that indeed if you have those two pictures on the right, okay, then try to think of the inverse, and you see right away with these simplest examples that you cannot possibly build the inverse, because why? Think about the first example. There is no inverse because why there is no
different results.
This because you got to reverse the arrows, right? And then well, where do you go from C? Do you go to A or you go to B? You cannot have if you pick one over the other, then you won't be able to complete all the trips. So, for example, if I pick A, then one trip I can complete. So if I go from C to A and then back, that's fine. Okay, and come back. But if I start at I start at B, then I will go to C, but then where I'm going from C? Back to A. Okay, and so the trip is not complete. Okay, so let me bring this. Okay, close enough. Okay, so once again, if I try to, so I'm trying to build inverse. Okay, I'm trying to build the inverse, and so we know that we're supposed to, well, anything at this point we don't even have to speak in terms of arrows. Arrow just helping us out. So what I'm doing here is I am trying to come up with the inverse, F inverse. Okay, F inverse. And so suppose I choose to go from C, F inverse goes to A. Well, maybe like this. Okay, from C goes to A. Then one of the trips can be completed from C to A and back, but the other trip has to be completed starting from B to C, and then I'm not going back. So this is the trip that is disallowed. It's not a round trip from B to C to A. Okay, so it falls apart. So that's why choosing A over B that does not work. Similarly, the situation I face when the function is not onto, I have the same thing, but the trouble is different. So this is the problem. I'm trying to build the inverse, a function that is not one-to-one. With the second one, the function is not onto. Well, how do I resolve it? I'm trying to build the inverse, and how do I build the inverse if it has to be defined on the on Y? B has to go somewhere and C has to go somewhere. Where do they go? There's only one place to go. To A, right? So Okay, so that's the only way for the inverse to exist, because there's only one candidate. Okay, so once again, if you try to go with the trips, you have trouble, because if I go from A to B, then I will return back to A. But if I start with C, as you can see, once again, I have a violation like this. I don't make a round trip. So if there is at least one non-round trip, then it's not the inverse. Okay, so building inverse in these simple examples, if you try to build inverse with all that we've got, there are too few choices in order for it to work, and you can just point out what your choice is, and based on that choice, the inverse is built, and then you can demonstrate that no, it's not the inverse. Okay, so so the theorem we're looking at is we have demonstrated right there, so that was just been proven yesterday. Okay, we certainly are not satisfied with that, because we want to. What's missing in the theorem? I mean, we have proven what I have written there is proven, but so it is certainly correct. If something is missing, I mean that it's kind of incomplete, and we want to make it complete. What's missing? The converse. So invertibility, in other words, the word that you use sometimes for the function, whether it has the inverse, is the same as one-to-one onto. So every invertible function is one-to-one onto, and every one-to-one function, one-to-one function is invertible. Okay, so then if these two conditions are satisfied, I then have to demonstrate that I have the inverse. Okay. So the proof isn't hard. Once again, based on what we've got, we are reversing arrows. So f is from x to y. Okay, it is one-to-one onto. Define f inverse of y. Define. So how do you algebraically reverse the arrow? So, like this. That's my arrow, goes backwards. But I don't want to rely on pictures. So what is it? Well, there is no formula, but it's an x such that, what? X and x such that f of x is equal to 1. That's the definition of the inverse. We try to stay away from definitions like that, because it is defined by defined indirectly, implicitly, and by means of a property. So when you define something by a property, there is a possibility then that property simply doesn't work. So we have to demonstrate that this makes sense to begin with. So we have to, when you're defining it, that first of all, there should be such an x, and there should be only one such an x. Okay, well, you can guess where it comes from. These two conclusions, they follow from those two assumptions. Okay, so you can say such an x exists because what? So there is an arrow, for each y there is an arrow going into it. Okay,
If F's onto.
F is onto. Yep, no, one at a time. F is onto. So such an X exists because F is onto, and then there is only one. Such an X exists because F is 1 to 1. Okay. So it goes back both ways, and then it is applicable to will be applicable in the future. Okay, so what else do we want? Oh, okay. Here's a theorem, another theorem. Well, maybe you can tell me first. The composition of two one-to-one functions is what? Is 1 to 1. You see why? So one-to-one functions, there is no like this. Okay, so so both functions don't do that. They might miss some of the outputs, but they all go like this. So if you continue going like this and they never meet together, then you have and you do a composition, you still have the same effect. So from X to Y, F and G. So then the composition will be this composition. G circle F will be as well 1 to 1. Okay, so this so part number 2, you can guess it is about onto, and the conclusion is the same. So the composition of two onto functions is onto. Okay, so once again, if F covers the whole Y and G covers the whole Z, then the composition will cover the whole Z. So so then this is your homework practice problem for you to at home to prove, to think about this. On the first try, you probably take some effort and some writing, but ultimately you will be able to put it in a very compact form, so like 2 lines of text ultimately. So it requires applying the definition of 1 to 1 3 times, and then for the second part, the definition of onto applied 3 times. But other than that, you don't have to invoke any theorems or anything like that. It's entirely definition based. Only definitions. But then in the future, we might actually use this theorem, and in fact, I have now a theorem in mind that I want to use, corollary. So I'm going to use this theorem. The composition of 2 bijections is a bijection. So once again, from X to Y, 1 to 1 onto, from Y to Z, 1 to 1 onto, then the whole thing is 1 to 1 onto. So why do we care about the last one especially? Remember that we use bijections to compare the number of elements in the set. So if there is a bijection, so we're talking about once again X, F, and Y and Z. So the F and G are bijections, which means that what does it mean? It means that the number of elements in X and Y is the same, and the number of elements in Y and Z is the same. What I want to conclude then, that the number of elements in X and Z is the same. Okay? So why is it important? Well, does this look familiar? Maybe. Well, not a lot of time ago. I transitioned from X to Y. Then I transitioned from Y to Z. I can transition, turns out, from X to Z. What is it? So once again, well, maybe like this. So I put them separately first. I transition from Y to Z under G, and then what I wanted to conclude that I transition from X to Z under G circle F. Okay, so where did we do these transitions? The transitivity property of equivalence relations. So, okay, so once you recognize that both of these are actually about transitivity, and so we prove transitivity, but transitivity of what? Of transitivity of bijection as an equivalence relation. So, in other words, bijections create an equivalence relation on sets. So that's what we are saying here. So once again, bijections form an equivalence relation on sets. In other words, X equivalent to Y, two sets unrelated to each other if there is a bijection. F from X to Y. Equivalence relation of all sets. So then all the elements of 5 elements will be equivalent to each other. All elements of 10 elements also will be equivalent to each other and none else. Okay? So, well, before we do anything with that, we have the transitivity. Transitivity, so that number 3. What else do we need? Reflexivity. So can you prove it? Reflexivity. Reflexivity, so, well, so in other words, X equivalent to Y implies that Y is equivalent to X. I'm sorry, yeah, sorry about that. Let's do reflexivity first. So reflexivity number 1, okay. So X is equivalent to X. Why is X equivalent to X? No, that would be circular. You gotta point out, the definition is 2 sets are equivalent when there is a bijection between them. You have to point out the bijection. So, you need to buy a bijection from X to X. What is it?
You just want to point out that X implies X, is that?
No. I just want a bijection between the set and itself.
That it's one-to-one and onto.
Right.
Bijection.
Yes.
Just state that, then I don't get it.
You have to be specific. Well, and it f of x equal to
X.
x. There you go. F of x is equal to x. It's called the identity function, by the way. One function from the set to itself is called the identity function. F of x is equal to x. It is a specific function, and to demonstrate that it's one-to-one onto it wouldn't take any work, right? Okay, so it doesn't have to. So sometimes we're lucky and we get an easy proof. Symmetry. So x equivalent to y, y equivalent to, then y is equivalent to x. Okay, so what do? Definition, so then jump to conclusions. X equivalent to y, so there's a bijection from x to y. Okay, so
Y implies X.
No, no. Y. It's equivalence relation between sets. So all of these are sets.
F of x equals y.
No. What you got to point out, we know that there's the bijection from x to y. You need to point out the bijection for y to x. What is it?
For y implies x.
No.
Would be f of x equals f of y.
No, f of x is f of x. F of x is given. So you remember, this is an implication. The first statement is given. The second is implied. Which how to prove it? We start with the second first statement. So we say there is a bijection. What it is, we don't know. Now we need to build a bijection between y and x, from y to x. This one is from x to y. We need from y to x. From x to y, f. From y to x, the inverse. The inverse. That's what we have been talking about. So then f inverse from which is from y to x is also a bijection.
Okay.
Well, that needs to be proven, but I hope it is believable. Okay, so as you can see how things come together into one place. So reflexivity was the easiest one, but by doing so we discovered this very important identity function that bijection naturally from the set to itself. Okay, then symmetry actually turns out the inverse function comes very handy. Because bijections have inverses, so the inverse has its role. It turns out that we can go back and we can go forth, and to confirm that the number of elements remains the same in both directions. And then the transitivity appears from this composition about one-to-one onto one-to-one composition of two one-to-one functions. Remember where the corollary came from? It came from this theorem. So two one-to-one functions give us one-to-one. Two onto functions give us onto, and then we had a corollary for bijections. So that's the transitivity for us. Also falls into our lap right away. And we have a bijections on the set of all sets. Not the bijections, but rather we have an equivalence relation on sets provided by bijections. There might be many bijections between sets, by the way. It doesn't matter. If there is one bijection, then we call them equivalent. And they are equivalent in many ways, if you think about it, because as one way we think about it is the number of elements. And at this time, we're not speaking necessarily of sets being finite. They could be infinite as well. But if we do think about finite sets, then we can see that indeed it is the number of elements is the characteristic of a set. Is what we extract. We take all the sets with this is how it actually works. So you take all sets X such that X is equivalent to set of 1, 2, 3, 4, 5. Okay, so all sets X that are equivalent to this particular set with 5 elements. We know that it has 5 elements. So how do we make sense of the number of elements equal to 5? And this is the answer. We split all the sets that are available in the world, so mathematical or otherwise, and as long as there is a bijection with a set of from 1 to 5, then we say, well, that it has 5 elements. And then what we do is from this infinitude of sets, we take with that property that the only thing that they have in common. So because the nature of sets is unspecified, what do they have in common? The number of elements. And then that number of elements finally becomes a number, and we can actually use it for our advantage to study sizes of sets, finite, and then later infinite too. Okay, so that's how things work out in set theory. So once again, very short theory, very short definitions, very precise, short proofs, and hardly anything that we bring into this other than logic. and now, so you don't need calculus, for example. Everything is self-contained. So every proof is pretty much relies on nothing but a couple of definitions. Even though the last one, I suppose, it brings into the play of one-to-one onto ideas, as well as the ideas about bijections, about equivalence relations. Okay, so then that's what we have right now. Just a minute. Okay, any questions about this? Okay, so bijections form an equivalence relation on sets. So just to give you a taste of it is that the elements 1, 3, 4, 5 has 5 elements, so that would be one equivalence class of all 5 elements, and then there will be equivalence class for elements with 1 element, then 2 elements, 3 elements, and then we know equivalence classes do not intersect, so you cannot have 2 sets with a different number of elements. Good. But then what we get to, following the same logic, with not the same logic, this logic, it continues on. What about we have infinitely large sets? So in other words, it's not equivalent, so X is called infinite. If it's not equivalent. So in other words, there is no bijection equivalent or equivalent to a set, to a subset, well, 1 n. Okay, so I point out the sets that we know to be finite, 1 through n. So specifically integers, we put the n integers in that set. So we know that is finite. So if there's a set which does not have a bijection from itself to a set like this, then we call that set infinite. Okay, so we do it in the negative. And then everything has to be proven. Z, Q, R are infinite. Starting naturally with Z, then you would have to demonstrate that Z is not a finite set. So you would have to demonstrate now that there is no bijection between Z and a set of n elements, no matter how large n is. Okay, so probably not too hard. Okay, so but we will postpone dealing with infinity until later. It is a hard topic, and on top of all the complexity of set theory, infinity, so it's counting to infinite is a challenge. So I'm going to do a bit more of just a bit more of set theory, and another construction of well, let me start with this domain codomain. So this is the domain X domain of a function, and this is codomain Y. Okay, so X and Y, and then I have my graph Y equal f of X. Okay, so this is when X and Y are both the real numbers or subsets of real numbers. Okay, so that's a calculus 1 situation. Then you go on to calculus 3, and you might be looking at, we already talked about that, so let's do more of that, into parameter curves. And this is the codomain, say a plane. So Y is a plane, while the domain X is a line. Okay, so and then you have a curve here. Okay, so and this is the graph, and that's the graph over here too. Okay, and then one more step. If we move on to functions of several variables, remember this. So this is the domain, x is equal to R2. Okay, and then the z-axis is y, which is R. Okay, and the graph is possibly a surface. Okay, so we're talking about functions from x to y, and I just picked three different examples of x and y, which you saw in calculus. So calculus 1, and then the other two in calculus 3. Okay, so input is a real number, and then output is a real number, or input is a real number, and output is a vector. Okay, and finally, the input is a vector, or just an element. Doesn't have to be a vector, a point in the plane, and the output is a real number on that vertical axis. Okay, but once again, this is the graph. So I want to talk about graphs. I want to talk about graphs in this more abstract set theoretic sense. Okay, so the question really becomes first, where does the graph lie? How would you characterize it, what we're looking at? We have x and we have y, right? But there is way more where the graph has to be located. Well, look at the first example. The graph lies where? Well, it doesn't have to be first quadrant, but rather it lies on the plane, right? It lies on the plane, specifically xy plane. And how do you build xy plane? You take the x-axis and y-axis, and then create pairs of xy's, right? Okay, so these are points xy is what the plane is made of. Now, if we look at the second graph, we have still x and y in a way, but the graph lies in this three-dimensional space. Not by coincidence, we have, look at the dimensions of the two spaces involved, x and y, dimension 1 and dimension 2, so 1 and 2 add up to 3, right? So that's why, so this was R2, the plane, this is R3, right? Where does R3 come from? Once again, 3 is equal to 2 plus 1. So the dimension of the domain, 1, and the dimension of codomain is 2. Okay? The dimensions being added up. So this one is 1 plus 1 is equal to 2. This is 2 plus 1 is equal to, or in chronological order, 1 plus 2. 1 plus 2, so the domain and codomain gives me the graph, the location for the graph. And finally, the last one is the total. The dimension is still R3, except this 3 is not made of 1 plus 2, it's 2 plus 1. Why? Because the 2 is the domain is 2, dimension of domain is 2, the dimension of codomain is 1. Okay, so in other words, dimension being added up. The trouble with adding dimensions is, however, that it simply doesn't work in set theory because there are no dimensions. So then we have to realize that it is about products. So plane R2 is equal to R cross R. Okay? To be explained, and space is R3, which is R2 cross R1, or R1 cross R2. So that's where you want to place your graph, because it's made of pairs x and y's. So you pair up x is here and y is there, and create a new space, create a new set. So that's what we're going to be doing next.